Hello, everyone. In this lecture, we're going to talk about support vector machines. Or SVM. And SVM could be a linear classifier, but it can also be a nonlinear classifier through the kernel trick. It could be either linear classifier or nonlinear classifier by the kernels. Admittedly, SVM nowadays is not as popular as maybe 10 years ago, but still, I think there are a lot of important ideas here, including how to do the optimization and how to do the kernels. So I'm still going to cover this topic in this course. So first, let's clarify that support vector machine is intrinsically a binary classifier. Although you can do it for multi-class situation, it's not an elegant model. So at this moment, we consider a binary classification. Okay. And as a general start, we also assume that the problem itself is linearly separable. Okay, so this is my assumption for, at least for this lecture. So let's consider x1, x2 as my features, okay? So I have a few features. I have a few data samples here, and I have another few samples, okay, here. So indeed, it's a binary classification problem. I have two classes, okay? This is the positive class, this is the negative class, and it's linearly separable. If I cut it off here, of course, I can achieve 100% accuracy, okay? So I point here as red, okay, I achieve 100% accuracy. And the support vector machine, this model is not a probability model. So I have no distribution. I have no probability assumption on either X or on target, no assumptions. But I have a heuristic saying among all the classifiers that can achieve 100% accuracy, some are still better than the other, okay? So one example is, so suppose the blue points are the positive samples and the red points are the negative samples, okay? So I would say this classifier, and I point to here as 1, okay? So it achieves 100% accuracy, okay, it's good. But I can try it again. I say, okay, maybe this is my classifier. Okay, this is my classifier, and I point to here, okay? It also achieves 100% accuracy on these data samples. And I can do more. For example, how about I have a classifier like this. So I say this half space is 1, okay? So this classifier also achieves 100% accuracy. But obviously, among these three classifiers, one is better than the other two, okay? Obviously, this is the best classifier that we would like to choose, right? Even if they achieve the same accuracy on these samples, it appears that this classifier is the more stable classifier because maybe next time you have some test sample and maybe this test sample is here, okay? Another test sample is here. Okay. Then with these test samples, okay, if you have this classifier, okay, it's predicted wrong, and it's also predicted wrong. But in here, okay, this test sample is predicted correctly, but this sample is predicted wrong. So our heuristic is this classifier is the most stable classifier, and it's probably the most generalizable classifier. It's intuitive, generalizable. And why? How can I formulate this intuition? The formulation is by the margin, okay? So let's consider the distance of a data point to this decision boundary, okay? How far is it? Okay, how far is it? For the first classifier, it seems like the data points are falling apart from my decision boundary. Okay, it's very far away from my decision boundary, and it appears to be the most stable one. But for this classifier, this point is close to my decision boundary. Okay, the margin is here, and even if this margin is large, this margin is small. Okay, and for the third classifier, it's even worse because the margin is small for both positive and negative samples. Okay. So this is the formulation of our intuition that we probably want to maximize the margin between the data points and the decision boundary. Okay. So the intuition is maximize the margin between data points, and decision boundary. And again, let's just consider a linearly separable problem. If your problem is XOR, for example, like this, you cannot have a decision boundary that you perfectly separate these four samples. We can still solve that by SVM, but it's not considered at this moment, okay? So the next thing is, how can I formulate this intuition into equations, and how can I solve that problem? So the formulation is, what is the distance between a point, okay, X, and a decision boundary here it's a linear decision boundary, so it's a hyperplane. Okay, maybe I call this hyperplane W transpose X plus B. What is the distance? The distance is actually, suppose this is X. You put your data sample, suppose this is a particular data sample, XM. So you just put your data sample into your decision boundaries formula, okay, and you divide it by the norm of your weights. And if you consider the distance, you take the absolute value because it can be positive or negative, okay? So suppose this is my vector W. So this is the norm vector. And if a point is in the half space that the norm vector pointed to, then it's positive, okay? It's positive. If it's in the opposite half space, then it's negative, okay? So the decision boundary is actually this. So this is the distance. So I can call it D for the M, okay, it's this. And how can I show it? So if you are not familiar with this equation, then you can probably refresh your geometry knowledge, or it's not very difficult to show that you first get this point. Okay, so what is this point? So I call it maybe X P projection or whatever. So I call this point P. Then this P satisfies this equation, so it should be W transpose P plus B equals 0, and so this vector should be X minus P. So this vector should be parallel to the W, okay? It should be the same direction as W. So I can say this times my W, the inner product of my W should be the same as X minus P, the distance times the distance of W. Then you see, you almost get it, right? This is my distance. Here you can say this is X transpose for a particular data point M, transpose W minus W transpose P. But we know W transpose P is B, okay? It's minus B. So W transpose P is minus B. So this gives me that the distance is W transpose. Anyway, you just apply some simple geometry knowledge and you will get that the distance between a point to a hyperplane is you just plug in the point into the formula for this hyperplane and you divide it by the norm of W. Because you increase the norm, it doesn't change the distance. And so you have to normalize it by the norm of W. Okay. And I would like to minimize the distance, okay? So I suppose, if this point is a positive data sample, okay, then it should be located in the half space that your normal vector points to. If a point is a negative sample, it should be in the opposite way, then it gives you a, W transpose X plus B is a negative number, right? So this can be unified as saying my distance. So let's suppose my target is either +1 or -1, okay? So this time my target is not 0 and 1. It's not 1 hot. It's saying positive sample is 1, negative sample is -1. Then the distance I can write it as dm Tm times W transpose Xm plus B divided by norm of W. Okay. And for positive sample, this is actually the distance, how far it is from the decision boundary when you go into the half space that your normal vector points to, right? And for a negative sample, it shows how far you go in the opposite way. But if you intrude the wrong decision boundary, then this number is negative, okay? So it shows it's undesired. And our goal is to maximize the distance, okay? But which distance? It only maximizes the smallest distance, okay? So this is the smallest distance, so I just maximize this distance, okay? And all other points, I say it's fine, okay? I only find the minimum distance. So that's why they are called the support factors. They support this decision boundary, and all other points are not immediately related to a decision boundary, right? So you are actually saying I'm maximizing the minimum distance of different data points, okay? So it's the maximum of the minimum over my distance, where the minimum is set in terms of different m's, okay? So I can compute the distance of different samples, and I'm going to tune my W and B to minimize this, okay? So it's actually saying maximize over W and B, minimize the m from 1 to m, this distance. Okay, so now we can solve this problem. We first find the minimum distance, you maximize it, you find the, based on the new weights, you find the minimum distance and you maximize it. It doesn't seem to be a very fancy approach because it's not convex and it doesn't guarantee that you'll converge very nicely, okay? And also the solution is not unique. Suppose my W star and B star is my optimum here. Then if I have any KW star and KB star for any K, let's assume it's greater than or greater than 0, okay? It's also the optimum, right? So I just scale the numerator and the denominator by K times, it doesn't change my solution. So this shows that if you directly optimize this, you don't have a unique solution and the optimization is not very fun, and you don't have a guarantee that it will converge nicely, okay? So that's why oftentimes we want to change the problem into a convex problem, if you can, and I will show you can, okay? But if you cannot, just like a neural network, okay, we still work with that. It's not a big problem, but if you can convert a problem into convex optimization, usually it gives you a better guarantee of the conversion or getting the optimum. First, we observe that we can actually make my solution unique if we impose a dummy constraint. So I can tell you a constraint, and that constraint is not necessary. But given that constraint, then the solution is unique, right? So the example is, I'm just writing an example. So the minimum of this function is not unique, right? You can have any y, but I give you a constraint. So this is a quadratic form in x, okay, but it's a constant in y, right? Okay. But if I give you a constraint saying, okay, x plus y must equal to 1, then you get a unique solution here, okay? If I give you another constraint, maybe y equals 2, then you get a constraint here, okay? So if I put one more constraint, then you cannot scale, then you get a unique solution. And that seems to be a first step. And what is that solution? So maybe I can say my w equals 1. But it's not good because I have to, even if you have w equals to 1, I still have two optimization process. I have to find the minimum and to find the maximum. And this is still not a convex problem when you consider the optimization for w. Okay, it's not good either. How about I say this equals to 1? Okay. If I say this equals to 1, then my optimization becomes maximum w and b 1 over w. And it's equivalent to say my minimize over w and b norm of w, okay? But I can also say w squared L2 norm squared 1 over w. Okay. Then if you minimize it, then you say, okay, w is 0. But this is incorrect because you haven't considered the constraint, okay? The constraint is subject to the minimum of 1 up to m Tn wx plus is 1, okay? So I have a constraint saying the minimum must be 1. Then with that constraint, I can optimize the norm of w. But it's still not very good because this constraint is the equality constraint. And I mentioned that if you consider convex optimization, the equality constraint must be an affine function, but here it's minimizing something, it's not good. So the idea now becomes, it's maybe the same as say minimize subject to Tm greater than or equal to 1. Okay. And obviously this is a sufficient condition. So it's a necessary condition. It's a necessary condition, but it's not sufficient, okay? So if I satisfy the minimum equals 1, then obviously everything must be greater than 1 for m equals 1 up to n, okay? But if I have this satisfied, it does not guarantee that my minimum equals to 1, okay? It's not guaranteed. So it's not necessarily sufficient. But we will show that for this particular problem, they're equivalent, okay? And the reason is we consider what is that constraint. The constraint, let's assume I have a positive sample for some m, okay. Tm is positive, so it's a positive sample. So this constraint actually says W transpose X plus B is greater than or equal to 1. So let's consider this is the B axis, and this is the W space, and maybe it's a high dimensional space, but I just plotted in a low dimensional by a line. Okay, so this is my W vector space. And what happens? So this constraint actually says, for one data sample, it actually says you must be greater than or equal to this, okay? So this is my feasible solution, right? So you can verify it, you say, if my W is zero, then, this term is 0, and, this is 1, okay? B equals 1. So this is my inequality, but this boundary is, I make the inequality as equality, okay? For any positive data sample, it must cross this point, okay? W equals 0 and B equals 1. And it must point to the feasible set must be the upper half space, because, if I have a larger B, then it's more likely to be satisfied, okay? And likewise, for a negative sample, if T equals -1, then I have a point here, and I have another constraint like this, and I'm pointing to the lower half space, okay? So this is a constraint for a negative sample. And now I take the intersection of all the constraints. My eventual feasible set is this, okay? This is my final feasible set. And if it's linearly separable, then it's non-empty. If it's not linearly separable, yes, it's probably empty, okay? So you say a point you go here and another point you go there. Then if you consider the feasible set like the blue, the green, and the black ones, then it's empty. There's no feasible set, it's not solvable. But if it's a linearly separable problem, the feasible set is not empty. And this is my feasible set. And what is my objective? My objective says my weights should be as small as possible, okay? The L2 norm of the weights should be as small as possible, so you get this point, right? It's the closest point to the B axis, because this is just the radius of in the W space, okay? So it's not the radius in the W and B space, it's actually the radius in the W space. Then you want to be as close as to the B axis, then you get this point. So this is your optimum solution. And when you get the optimum, it's at least on 2 decision boundaries, okay? So if it's on the 2 decision boundary, then the inequality greater than or equals to 1 is 1. So that's why it shows, if you optimize this problem, it will automatically satisfy the minimum will be 1, because you will touch this boundary, okay? So it's a little bit confusing, but the main story up to now is saying, if I would like to optimize the minimum of this equals to 1 for this particular problem, it's equivalent to say, I say every constraint is greater than or equal to 1. Okay, because I'm minimizing W, and you will push W closest to the B axis, and you'll get this point. If you are on this boundary, on this line, on these hyperplanes, then the minimum is indeed 1. Okay, so this is the story up to now. Then I have my optimization problem. As minimize the L2 norm of my weight subject to these things. So what is that? Where's my optimization variable? My optimization variable is W and B, okay? And this is actually an affine function of W and B. And an affine function is a convex function. and this is a convex constraint. Okay, so this is a inequality constraint, but this is convex, so it's a convex optimization problem. Okay, so this is convex optimization. So from now, we just derive the intuition. We just formulate the intuition into math. We say we would like to maximize the boundary between the data points and the decision boundary of your classification. And this can be represented by this equation, okay, by this formula. Okay. We can maximize the minimum distance, okay? And the solution is not unique, and we can impose an arbitrary constraint saying, okay, the minimum distance, ignoring W itself, okay? The minimum distance unnormalized must be 1, okay? And then I can relax the minimum equals 1 and say all the points is greater than or equal to 1. Then I convert this problem into a convex optimization problem. Next, I will give a systematic review of the convex optimization, which will be used to solve this problem, but will also be useful for other problems. So let's consider an optimization problem. Can be represented as f0 of x minimized over x subject to fi of x less than or equal to 0 for I equals 1 up to n, okay? And hi of x equals 0 for I equals 1 up to n, okay? So this is the generic formula for an optimization problem, okay? For any optimization problem, I can always say that, right? So a convex optimization problem means you optimize a convex function, convex objectives on a convex set. Okay. So basically it says this is your x, and this is your maybe f of x, f0 of x, which is your objective. This objective must be convex. It cannot curve down. And then your feasible set, your constraint must be a convex set. So you cannot say my constraint is, suppose this is my x, my feasible set is this set, okay? Then it's not convex, okay? So the convex optimization is essentially a convex objective on the convex set, which tells us that fi must be convex functions for I from 0 to m, okay? So for the objective and for the inequality constraints, they must be convex functions. And for h of I, they must be affine functions. If you have a convex function for the equality constraint, then the feasible set is not convex, right? So if you say x1, x2, I say my feasible set must be on this quadratic form in the x1, x2 space. Then it's not convex because the middle point is not in your feasible set. So this shows that your equality constraint must be affine and your inequality constraint must be convex and must be less than or equal to 0. And your objective must also be convex, okay? So this is the general form of an optimization problem. And what does it mean by convex optimization? The next thing is dual problem. So I think we mentioned the dual problem in the soft penalty and hard constraint. So I'm just going to give the definition again, the dual problem. So I can construct a Lagrangian Lagrangian is basically you make the hard penalty as soft constraint, okay? And for convex problems, the hard constraint and the soft penalty, they are equivalent. So I construct the Lagrangian as Lagrangian is f naught of x plus the summation over I from 1 to n. I have n many inequality constraints, lambda I, fi of x plus n nu I, hi of x. Okay, I have every inequality constraint and every equality constraint as soft penalty. And here I have n many, and here I have n many, so I have m and n, okay, summation. Where for each of the equality and inequality constraint, I have a multiplier, which is lambda and nu. So now the Lagrangian becomes a function of your x and lambda and nu. Here the lambda is a vector, and nu is also a vector, okay? So the lambda is lambda 1 up to lambda m. Nu is nu 1 to nu n, okay? So this is the Lagrangian. And the Lagrange dual function is I eliminate the primal variable x in my Lagrangian, okay? So the Lagrange dual function is g lambda nu as the infimum over x, Lagrangian of x nu lambda nu, okay? So this is the definition of Lagrange dual function. And finally, I have the dual problem. The dual problem is I would like to maximize g lambda nu such that my lambda must be positive, okay? So it shows that for every lambda I, it must be non-negative, okay? Greater than or equal to 0. So this is my dual problem. So I first construct the Lagrangian, and I can construct the Lagrange dual function, which is the infimum. Infimum is just minimum, okay? So you can just think of it as a minimum of this. And then I would like to maximize the Lagrange dual function by optimizing lambda and nu such that my lambda has to be non-negative. So this is the definition of the dual problem. So for the original problem, a generic optimization problem looks like this. I can say this is the primal problem, okay? And this is the dual problem. Then I have a few dualities. So the first is the weak duality, okay? So I would say D star is the optimum or the optimal value for the dual problem. And P star is the optimum value for the primal problem. And dual problem must be less than or equal to the primal problem for any optimization problem, no matter whether it's convex or not, okay? So the dual optimal value must be less than or equal to the primal optimal value. And this can be shown by taking the definition. What is the dual problem? The dual problem is I maximize over lambda nu, where lambda is greater than or equal to 0, g lambda nu like this. So I say for any lambda nu, I have g lambda nu is the minimum of x, Lagrangian of x and lambda nu, okay? Then this is the minimum of my Lagrangian, where X is the primal feasible solution. But what if my X star, suppose it's the primal optimum, then it's, of course, within the set that you consider for the minimization, right? So I can say this is actually less than or equal to X star lambda nu, where X star is the primal optimum. Primal optimum. Okay. So by definition of the Lagrangian, it's just the F naught of X star plus the summation over 1 up to m lambda I fi of x plus the summation over I from n nu I hi of x. Stop. Okay. And I know that X star is primal feasible. So this is 0. And this is less than or equal to 0. And I know that my lambda and nu are dual feasible. So this is for any lambda, which should be greater than or equal to 0. Because I consider a dual feasible solution for lambda and nu. Then this is greater than or equal to 0. Okay. So this term, the second term must be 0 because h is 0. But this term, one is greater than or equal to 0, the other is less than or equal to 0. So this term is less than or equal to 0. So you are saying g is less than f of x minus something, okay, minus a positive number. So it's less than or equal to f naught of x. Right? For any dual feasible solution, g lambda nu is less than or equal to f naught x star. Then obviously my dual optimum must be feasible. So it must satisfy this, then it's less than or f naught of x. Sorry, this is going to be a very lengthy discussion, so just bear with me. The next thing is strong duality. Strong duality means the dual optimum value is the same as primal optimum value. So it says the primal problem, minimizing something, is always better than maximizing the dual problem. Okay, the maximizing the dual problem is minimizing the primal problem. But for some problems, the gap is 0. Okay, so for some problems, the gap is 0. So in this case, we say the strong duality holds, and the gap here is called P star minus D star. It's known as the duality gap. So strong duality says D star equals P star under some conditions. Or with some properties. So this doesn't necessarily hold, but for weak duality, it must hold for any optimization problem as shown here. So when does the strong duality hold? The first thing is the Slater's condition. It's not proved, but I'm just going to say it again. For any convex optimization problem, if it's strictly feasible, then it's strong duality holds. Okay. It says there exists some lambda and nu and x where you achieve the primal minima and achieve the dual optima and they touch. Okay. The other is the KT condition. Now I need a cheat sheet. So it's Karash, Kuhn, Turker. Okay. So these are the 3 authors who discovered the KT conditions. So KT condition is a necessary condition for any optimization problem. for any differentiable objective. Okay, so your objective must be differentiable. Otherwise, I will use the derivative information that it doesn't hold. But for any differentiable, for any optimization problem with differentiable objective, then it's a necessary condition. So it's not sufficient, which means if strong duality holds, I must have the following property. So this is the definition for necessary conditions. I must have the following property. I have 5 conditions for KAT, but they can be remembered by groups, okay? So the groups are primal feasibility. The other is the dual feasibility. And the third is the KAT complementary condition. So this is interesting, complementary. And the third is the gradient vanishing of the Lagrangian, okay? So essentially it says if X star, lambda star, nu star are the optimum for primal and dual, okay, respectively, with primal optimum value is the dual optimum value, okay? So it means if they are the optimum values and the duality gap is 0, then I have these conditions. So since they are the optimum values, so I must have all the primal constraints satisfied. So it's fi of x is less than or equal to 0 for I from 1 up to m, okay? And hi of x equals 0 for I from 1 up to n or m. So let's see what is our index. mn, okay? We have n many inequality constraints and we have n many equality constraints. So this is the primal feasibility. Dual feasibility is lambda I should be greater than or equal to 0 for I equals 1 up to m, because the dual constraint is only for the inequality constraints, okay? And the third thing is the KT complementary condition. It says lambda I fi of x must equal 0 for I equals 1 up to m. This is because we consider the Lagrange dual function lambda nu for any lambda greater than or equal to 0 and nu, which is a real vector, okay, is the minimum over x f naught of x plus summation from I from 1 to m fi of x lambda I plus nu I hi of x. And I know that it must be the same as my primal optimum, okay? Here I know the primal equality constraint must be 0, okay? The equality constraint must be satisfied, so I can just ignore this term. And for the remaining term, you know, the minimum of this term and this term is less than or equal to 0, right? But I know this is the primal optimum, and here you subtract a non-positive term, and they're still the same. So this term must be 0. Okay, so this tells you the KT complementary condition. It says either your Lagrange multiply is 0, or your inequality constraint satisfied as equality constraints. Okay, so these two factors must be 0 for at least one factor. It's possible that 2 factors are 0, but at least you require that one of them is 0. Okay. Going back to the SVM case, I have a few points for positive samples. I have a few other points for negative samples, okay? So eventually we will show that either a point is on the margin, okay? On the margin, which means your f of x is 0, okay? So if we apply the kt to the SVM problem, if a point is on the margin, then it becomes the support factor, then the inequality constraint must hold as equality constraint, and it has a non-negative weight. But if a point is off the margin here, the point is off the margin here, they are not touching the margin, which shows that the inequality constraint holds strictly, then its Lagrange multiplier, which is lambda, is 0, okay? When you translate the result into the SVM case, it says this point has no immediate effect on the decision boundary, okay, because its weight is 0. If it's on the margin, then the inequality holds as equality, then there could be a non-zero weight for that, okay? So this is basically the story of the support vector. So the points on the margin, the points on the margin are the support vectors. But in here, it's the KT complementary. And finally, the gradient must vanish at the optimum. So the Lagrangian gradient with respect to x of the Lagrangian of x, lambda nu, when you evaluate the gradient at the optimum, it's 0, okay? Because you're optimizing the dual problem, there's a minimizing of x, okay, over the Lagrangian, then you are taking the optimum, so the gradient must vanish, and it only holds for differentiable objective. If it's not differentiable, then it doesn't hold. But in here, we consider differentiable objective just like the SVM, then we have the gradient vanishing condition, okay? In general, I have 5 conditions, 1, 2, 3, 4, 5, grouped into 4 categories. They are necessary conditions. If I have the strong duality holds for any differentiable objective optimization function, then these must hold, but not vice versa. If you find some points, these things hold, it may not be the optimum for the primal or the dual, and the gap may not close, okay? It's only necessary. KTs are necessary conditions. But KD is sufficient for convex optimization. Okay, so it says if there exists some x tilde, lambda tilde, and nu tilde such that they satisfy these constraints. Again, primal feasibility, dual feasibility, KD complementary, and gradient vanishing. So it says fi of x tilde less than or equal to 0 for I equals 1 up to m, and hi tilde equals 0 for I from 1 to n, and lambda I is greater than or equal to 0 for I equals 1 up to m, and KT complementary, lambda I hi of x is 0 for I from 1 to m, and the gradient vanishes at, okay, here is all tildes, okay, equals 0. So here all of them are tilde. So here the x is a function variable, but I take the derivative, evaluate it at x tilde, but lambda and nu are the optimum, okay? Then strong duality holds. With x tilde, lambda, nu tilde being the primal and dual optimum respectively, okay? Why? We know that the Lagrange dual function x lambda nu is the minimum over x f naught of x plus summation over 1 up to m lambda I hi of x plus summation I from 1 to n nu I, so this is f hi of x. Okay, this is the definition of the Lagrange dual function. Then I know that the gradient vanishes for the Lagrangian. Okay, so when you do the minimization, and this is a convex function, right? This is convex. This is also convex. This is affine, which is also convex. The entire Lagrangian is convex function. Then if the gradient vanishes at a point, the gradient is 0, then the minimum is achieved at that point. Okay, so it's achieved at the point here. And I know the primal feasibility, this term must vanish, okay? This term must be 0. It's given by the primal feasibility. And this term must be 0 because of the KT complementary, so it's also vanishes. Okay? But I know that, so this tells us that, so everything here is tilde, okay? So this tells us that lambda tilde, nu tilde makes the Lagrange dual function touches some value of the primal. But I know that the dual function must be always uniformly less than or equal to the primal function, right? Primal objective. If they touches, then the optimum is achieved for both the primal and dual problem. So this shows lambda tilde and nu tilde are the optimum for the dual problem, and here x tilde is the optimum for the primal problem. Okay. So basically, we are done with a generic review of a convex optimization. A convex optimization is optimizing a convex objective function over a convex set. We construct the dual problem by maximizing the dual variables of the minimum over the primal problem of the Lagrangian, okay? Where the Lagrangian is the original objective penalized by some soft penalty of the constraints. Then we show that the primal problem and the dual problem are closely related. First, the dual problem must be less than or equal to the primal problem for any optimization problem. But under some conditions, they can touch, okay, they touch. And one of the conditions is the Slater's condition, and the other is the KD condition. But usually KD condition is the necessary condition, but for convex optimization problems, it's also sufficient. Okay, so this is the story. So now we're going to use the general tool for convex optimization to solve the problem for SVM. Okay. So for SVM is to minimize over W and B half W square subject to okay. You know, if you divide it by the norm of W, it's the distance. But I consider the numerator and say the minimum of the numerator is greater than 1, but I ignore the constraint and it will be automatically satisfied. If you start solving this problem, then you know the derivation is almost always wrong because it's not in the canonical form. It's not less than or equal to 0. And if you write things like this, when you compute the Lagrangian here, it's all of a mess. It's almost always wrong. So you must change it to the canonical form, which is 1 minus Tm W transpose Xm b is less than or equal to 0. Okay, they're equivalent. And I must write the constraint and the objective function in the canonical form. Okay. Then everything is the standard. Okay, so let's do the Lagrangian of x lambda nu. By the way, I don't have nu because I don't have equality constraint. I only have inequality constraint. How many constraints do I have? I have 1 up to m constraints. Okay, 1 up to m constraints. Lambda, oh, I typically call it alpha. M. One minus Tm. Okay, it's a more standard notation for SVM, but it's just the lambda in the generic formula for convex optimization we just talked about. So it's alpha. Now I'm going to take the partial derivative of my Lagrangian with my primal variable, and I would like to set them to 0. Okay, so I know that this problem is convex optimization, and suppose you are considering a linearly separable problem, and it's strictly linearly separable. Okay, it's not a point like you have a boundary. Some of them are positive, some of them negative. Then it's not strictly separable. But we consider a problem that's strictly separable, then it satisfies the Slater's condition. We know that the strong duality must hold. Okay, and if the strong duality holds, then I'm using the KT necessary conditions to find the solution. Okay, I don't have to use all of them, but as long as I can use some of them and find the solution, then I get it. So let's set the derivative to 0. Okay, and I also have a constraint such that alpha m must be greater than or equal to 0. One gives us me what is the partial derivative with respect to w as a vector. Okay, so here it's the partial derivative of w transpose w. Okay, when you do the derivative, it gives you just w. Okay, so you say just w plus. Okay, here I have 3 terms. One is the alpha term, the other is the alpha Tw transpose x, and the third term is the alpha Tb. Okay, and only the second term involves w because all other terms are a constant of w. So I only need to consider the second term, which is the alpha times minus Tm times w transpose x. Okay, so it's the alpha minus Tm xm. Be careful, what are the vectors and what are the scalars, okay? Xm is a column vector and W is also a column vector and they have the same dimension, okay, perfect. I set it to 0, okay? And I don't know how to use it. Let's just put it here. And the second constraint tells me that the partial derivative of the Lagrangian with respect to B is 0. So the first term is a constant of B. The second giant term has 3 small terms, and only the third term involves B, which is here, okay? So it's the summation So here minus cancels out with that minus, so I only need the positive Tm set to 0. So something strange has happened. Here I take the partial derivative with respect to b, and this term does not contain b, okay? It gives us one more constraint about alpha. The reason is we're talking about the minimization over x, over the primal problem, which is w and b, the Lagrangian, okay? The maximum over the alphas, okay? And alphas must be greater than or equal to 0, okay? For the alpha vector, that is script greater than or equal to 0, but for every alpha I, it's scalar greater than or equal to 0. The Lagrangian over WB is the primal variables, and the alpha are the dual variables, okay? I'm maximizing over the dual problem of the minimum of the primal problem of my Lagrangian. But if this constraint is not satisfied, we observe that the Lagrangian L is a affine function of B, okay? Then the minimum can be minus infinity, right? I can tune my B to make my Lagrangian as small as possible because suppose I have either plus or minus maybe k times B. It's an affine function of B, okay? K is non-zero. K is just this term, okay? This is my K, right? Then I can make my Lagrangian as small as possible, and it can be minus infinity. But ultimately, my optimization is over alpha to make the minimum of my Lagrangian maximum. But minus infinity is definitely not maximum. I will not consider that, right? So it gives me one more constraint on my alpha. The alpha, only if your alpha satisfies this constraint, it can make my minimum of the Lagrangian as large as possible. If you don't have this constraint satisfied, then the minimum of the Lagrangian is minus infinity. Then it will not be selected during the maximization of alpha procedure, okay? This tells me that if your Lagrangian is an affine function of a variable, then when you take the partial derivative, it gives you one more constraint for the dual variable. I know it must be satisfied. Then what is my Lagrangian? Lagrangian is this term, okay? The idea is eventually we're going to minimize my Lagrangian over W and B and maximize over my alpha, okay? But based on the KT necessary conditions, I can probably eliminate W, okay? So here I can represent W with alpha. Then I can plug my W into my Lagrangian, which is the analytic form for this, okay? Then I seek the optimum for the dual problem, which is to maximize the minimum of the Lagrangian. So this is the plan. So the plan is from 4, we have W equals summation over 1 to M, alpha M, T M, X M vector, okay? Then put 6 into the Lagrangian. This is half. This is W transpose W. I'm only considering the first term at this moment, okay? It should be plus something. I consider it later. W transpose W is, okay? So this is the summation over I can put my transpose immediately before the vector. Okay, only x is the vector, all other things are scalars. Here, I mean, of course, it's also the summation over m, but here the m is the dummy variable, and to avoid confusion, I say this m is n, okay? A alpha n, t n, x n, okay? This is only the first term, okay? We haven't tackled the second term yet. So the second term, so I can write it out by saying the summation over 1 alpha n, alpha m, t n, t m, x n transpose x m, or x m transpose x m, it doesn't matter. Plus the second term. Okay, I promise you that there's some inner product here. Now it comes the inner product, but we will not touch this in this lecture. Let's continue working with the second term. Again, to avoid confusion, when I plug this term into the Lagrangian, I'm using n, okay? Otherwise, it will be conflicting with this m. Or I can expand this term. So I consider the second term, so I haven't put it into the giant Lagrangian term, so I can expand it as this is minus. Okay. But we know that the summation over alpha t must be 0. The summation over alpha t must be 0, okay? But b is a constant, so I can pull b out, and then this summation must be 0, so this term is 0. I even eliminate b in the Lagrangian. Okay, so xn transpose xm is almost the same as xm transpose xn. And magically, when you put this term into that term, so I can just copy it. Okay. Magically, this term is the same as this term, except the coefficient is different. Okay. So I'm going to say this is minus half sum over alpha n Tn Tm xn transpose xm. It doesn't matter whether n comes first or m comes first, but this is just the first term plus. Okay, this is my Lagrangian WB alpha with my primal optimum computed analytically. Okay, then my dual problem is to maximize the Lagrangian. The primal variables has already been eliminated due to the analytic computation of the gradient vanishing. And then I'm going to maximize this, which is to maximize this term subject to, first, I have the alpha must be greater than or equal to 0 for any alpha I, okay? Second, I have constructed one more equality constraint, which is this. Summation over m, alpha n Tm must be 0. How to solve this form? So this is a quadratic form of alpha, okay? We make things even simpler. Originally, we have a convex optimization, but we have esoteric constraints. After I transform the primal problem into the dual problem, they are the same because of the Slater's condition, or in the strictly feasible convex optimization, they're the same. And I can just solve the dual problem, it gives you the same as the primal problem. But then the problem becomes even simpler. It gives you the quadratic form of the dual variables. It's the alpha n, alpha m, and here is the alpha of some variable, except that we have some constraints. Alpha must be positive, and linear form of alpha must be 1. Okay, so this becomes a relatively simple optimization. But specifically for SVM, people usually use SMO algorithm, which is the sequential minimum optimization. It's specifically for SVM optimization, okay? Specifically for SVM dual problem. So the main idea is I can pick 2 alphas at a time, okay? And then I represent one alpha with all other alphas, right? Then I can eliminate this equality constraint. Then I optimize the other alpha. This is a quadratic form of a scalar variable, okay? A single variable. This is much simpler to solve than a high dimensional case. Then I optimize that alpha. If that is not satisfying this constraint, I just put it back. I just project it back into the feasible set. Okay. Then I pick another 2 alpha to minimize it. So it's known as the sequential minimization optimize. It's known as the sequential minimum or minimal optimization. Loop until convergence. Pick alpha I and alpha j, 2 alphas at a time, okay? It's one iteration in the loop. Represent alpha I with all other alphas, okay? All other alphas. So you eliminate alpha, okay? Then I optimize the Lagrangian with respect to alpha j only, okay? If you represent alpha I with all other alphas, you eliminate this equality constraint. Then I pick another alpha and I optimize the Lagrangian with respect to that single variable, okay? It's just, it's something like minus axb x squared plus bx plus c or something like this, okay? So, you know, if you are minimizing this term, then it's plus, okay? A is positive, but here you are maximizing the Lagrangian, so A is negative. But anyway, suppose we are doing minimizing of something, then you can get this term very easily, very cheap by an analytic form, okay, of one update. Then I check alpha j and alpha I, okay? If alpha j is less than 0, then I set as alpha j equals 0. And if alpha I is less than 0, then set alpha I is 0, right? Because you still have the equality constraint, and that cannot be easily resolved. By the way, this is a constraint optimization, and one way to solve the constraint optimization is you construct the Lagrangian. Okay, you construct the Lagrangian of the Lagrangian and you solve the dual problem. But unfortunately, if you solve the dual problem of the dual for the convex optimization, you are going to solve the primal problem. Then you have done nothing. You go in the loop and then you go to the origin. Okay, it's not what we desired. So we're just going to directly solve this problem by the SML algorithm. You pick two alphas at a time. One is to be eliminated and the other is to be optimized. And you temporarily ignore the inequality constraint, and you solve the variable to be optimized in an analytic way. And then you check whether the inequality constraint is satisfied or not. If it's not satisfied, you just project it back, okay, into the feasible set, which is they must be non-negative. You just set it to 0. Okay, we solved alpha. By doing this, I will solve the alpha star for different m's, okay? So I don't have a closed form solution, but I have a optimum alpha. Then what? Then I'm going to solve the primal W as well, and the primal B, the primal variables as well, okay? And that is actually not necessary. So, but I'm going to give the W and B anyway. So here's my constraint of W. W must be this, okay? B is a little bit tricky because I don't see any B here. Okay, I don't see any B here. I don't see any B as an equality constraint, but B will be the minimum such that make the inequality constraint as equality. Okay, so the minimum B make this inequality constraint valid. So this can be actually written as Tm double transpose X m minus Tm. Okay, why not? Let's say plus Tm B less than or equal to 0. For positive samples, it's going to be T is 1, so it's going to be B is less than or equal to, what is funny is it should be W transpose X plus B. But I still made my derivation correct. And the main reason is B is an affine function. When you take the partial derivative with respect to B, it should be either positive or negative. And eventually, do you remember we have this term, eventually it's 0, right? It gives you one more constraint, and the coefficient for B must be 0. Otherwise, the term, regardless of its plus or minus B, the Lagrangian will not be the maximum, okay? So it can be minus infinity. So eventually it gives you 0. So I don't have to consider whether it's plus B or minus B. But if you want to derive B, then you must be careful whether it's plus B or minus B, okay? So sometimes it happens that, after some derivations, you had your derivation wrong and still you can get the same result. And here's how. But if you correct this thing, then I can correct this thing. And then I can say for positive sample where Tm is 1, what happens? B should be greater than or equal to this, okay? Am I right? So for positive T, I know that Tm is 1. It doesn't seem to be correct. It should be 1 minus. But for negative, so I write it here, okay, it's ugly, but for negative samples, Tm is minus 1, so B should be 1 plus W transpose X. Less than or equal to but this time B is minus 1, so B is minus 1. So B is the less than or equal to minus 1 minus W transpose XM, okay? So in general, I can say B is the minimum of Tm is greater than or equal to 0, 1 minus Wxm, or I can say it's the maximum Tm less than or equal to 1 minus 1 W transpose Xm. Okay, I think it should be correct. So the target is either 1 or it's minus 1. And if it's plus 1, then it's this term. It's minus 1, it's that term. And I take the average. But in general, you can also consider all the points, all the points that alpha is non-zero, then you compute it for B, okay? For any points, for any m, alpha m is non-zero, then the inequality constraint must hold as equality constraint by the KT complementary condition, okay? For any point, this must hold. Then the inequality constraint, which is Tm W transpose Xm plus B must be greater than or equal to 1. Okay. Then you can use that constraint it must hold as 1, okay? Then you can use this constraint saying, okay, am I right? I'm going to make a mistake again. Oh, no, this term, okay? So, I mean, Tm must be either 1 or -1, so Tm just here. And then if you move it here, then -xm, okay? This must hold for any m with alpha m is not 0. But if it's 0, then it's not a support factor, okay? Then the b is not directly associated with that. So basically it says, these are my data points, and this is my decision boundary. And if you use this equation, I'm using the closest point to compute the decision, to compute the b, okay? But maybe you have 2 points that are both support factors. It's possible, right? Without this point, I may shift my decision boundary into here, okay? But with that point, my decision boundary is here. So you can use these 3 points to compute b. Then, b is this is b, is the average of number of alpha m is not 0, okay? All of these 3 points are my support vectors, then Tm minus xm, okay? Basically, the process of computing the b, okay? B is just the point, determine the shift of the decision boundary. It can shift around and it's in the middle. Okay, and this should not be confusing. And sorry for the derivation. I almost messed up the derivation, but fortunately, it's only just a bias term there, then it doesn't matter too much. Good. Decision rule. So I'm actually saying, this is my W transpose X plus B, okay? This is the summation. So the decision rule is W transpose X plus B. If it's greater than or equal to 0, then my output is 1, otherwise it's -1. So I can say my decision boundary is W transpose XB equals 1, okay, for a particular sample or for a new sample X. Then if you consider the B's, the W's here, okay, W is actually the summation over M from 1 to M alpha M T M X M X new star, okay, transpose. So I need a transpose here, plus B. B is just a term, okay? You can think of it as a constant. So I can say B is actually a number, okay? Maybe 0.3, okay? So this is B. You can just think of it as a number. So eventually we find that the decision boundary is only relevant to the inner product of one data sample and your new data sample, okay? And especially, you only care about the data samples whose alpha is not 0, okay? You only care about the data samples that are support factors. If it's not support factor, then I don't care about that, okay? And my training is the same. So my training, you only care about the inner product of your data, right? The dual problem is only the inner product of your data. This tells you that if I plug in a new inner product here, it may not be the L2 induced inner product in the original space, then I can transform my data sample in a higher dimensional space, or in a different dimensional space, then it gives you a nonlinear classification in the original space. Okay. But this will be our next lecture. I'm also going to tell what if my problem is not linearly separable, but the decision boundary or the Bayes classifier is still a linear classifier, or a linear classifier is still a good trade-off between bias and variance. But my data sample contains noise and it's not linearly separable. But we must have a soft margin saying that you can intrude the margin, but if you intrude the margin, then you have a penalty. And then I can still have a optimization almost in the same form, but it's more flexible. It can handle the noisy case. And I will talk about nonlinear classification by the kernel trick in the next lecture. Okay, see you next time.